chance for me to still talk about my work here. And so our work is about bargaining game in evolutionary game theory, and it is agent-based simulation. Basically, we just simulate a population of agents. They play the repeated bargaining game, and then we let the population evolve to see what kind of strategies survive after long terms. And bargaining behavior is a very important behavior in the social science and economics. You can think about the situation of worker and managers negotiating salary, or between buyer and seller. They try to set the price, divide the distance between the willingness to pay and the willingness to sell. And so this game is about the tension on how the benefit should be divided between two parties. It is different from the prisoner dilemmas in the sense that in the prisoner dilemmas, we want an outcome that is not an equilibrium. But here in this kind of non-zero sum game, we want an equilibrium to happen. But the tension comes from the fact that we both want to push the dividing point toward our own advantage. So we run the simulation in two settings: the one-shot and the repeated interaction. In the one-shot interaction, the agent, after they are matched, they will play the game for just one time. And so it resembles the situation of the game is played between two strangers or anonymous matchings. However, in the repeated interaction settings, the agents, after they are matched, they will play the game for multiple rounds. And so you can think about your business partners or your colleagues or your friends. Think about people that you can have enough data history to form expectation on how they will behave in a particular situation. That is the kind of repeated interaction we are talking about. And so the motivation of why we are curious about the bargaining game is that in a situation that we need cooperative behavior, like that is represented by the prisoner dilemmas, we can see that if the game is played for just one time, then everybody, in fact everybody's. However, with the possibility of tomorrow, then people start to cooperate and the societies can prosper. And so we ask the question of what about the bargaining game? So in the situation of the conflicting interest, when in the one-shot game, the 50-50 division is quite stable in the literature. That is the real result in the literatures. However, we can see that in realities, different societies have very different way to divide the pies. So the hypothesis of our work is that it is the repeated interaction that help to stabilize the cooperative behavior, but it is harmful for the fair behaviors. So we used a very simple version of the bargaining game, which is the Nash demand game, in which two players divide a pie of $10. So each can claim a high or medium or low fraction of the pie, which is 8, 5, and $2 out of 10. And if they are compatible, then they get what they want, otherwise they get zeros. This game has 3 Nash equilibria here and also 1 mixed Nash equilibrium. So for the two settings, the strategy set is also very different. For the one-shot game, there are only 3 possible strategies, and we can easily calculate the stable strategies, and I will show the replicated dynamics of this game later. However, in the repeated game, the number of strategies grows exponentially with the number of rounds to be played. For example, with just 10 rounds, then we have 3 to the power of 10 possible strategies, and it will be impossible to calculate the replicated dynamics, and so we decide to run a simulation to see what happens. And so in the repeated, we need the strategy representation in the repeated game, and we represent the strategies by finite state machine. A finite state machine is a machine that has a finite number of states. So, and they have transition rules to move between states. And here, the first machine here on the screen is very simple machine. It has only one state of play mediums, and its transition rule is also very simple. Whatever the other does, it will stay in the state of play mediums. And I show here 3 unconditional basic machine of this repeated games. And this is a bit more complex machine. It has 3 states to play mediums, high and lows, and its transition rule is like this. Initially, it's play mediums, but from the second round onwards, it played best response to whatever the other plays in the previous round. And so what does it mean? We will match it with all high machine to see what happens. So in the first round, because this accommodating machine claim medium and the all high machine claim high, then they are not compatible and they both get 0. However, in the second round, the accommodating machine will just retreat to claim lows, so they are compatible. And it will happen like that for the rest of the game. So now I will talk about the simulation. Imagine a world with many slots, and so we can populate it with agents, and the agent will adopt the strategies to play. And the agent here is not actors, they are just machine automatons. They do agencies, we give them a strategies, and they will play by the book until they terminate. So in the range of the sophistication of agents, this kind of agents is a Pavlovian type. And I also like to note that the reinforcement learning that we are trying to mimic is, the adaptive learning we are trying to mimic is the reinforcement learning based on aspiration. And this is, we follow the Vega Redondo textbook, and I will cite at the end of this presentation. And the dynamics that we try to replicate is the replicator dynamics. Just some very brief information. Okay, so because we will run the simulation in an evolutionary style, I would like to speak a bit about the evolution ideas. So evolution has two sub-processes, the selection and mutation process. The selection process is just to select the fittest strategies, and the mutation is to keep adding new strategies into the selection pool. And we will run simulation of many cycles. Each cycle will have 3 phases: matching phase, learning phase, and the mutation phase. This is the matching phase. So in the first cycles, we generate many random strategies, and each agent will adopt them. And then we match agents randomly in pair to play the Nash demand game repeatedly, and then we collect the payoff sequence and take the mean of that to calculate finite vectors for the whole population. So these finite vectors of the whole population will be used in the learning phase. In the learning phase, a small fraction of the population will be allowed to change the strategies, and so they will just look at the finite vectors. So technically, they randomize over the finite vectors. The result is that if a better strategy will be more attractive and will be more likely to be chosen to appear in the next cycles, so it will be more popular in the next cycles. We can see that in the pictures, one more agent is using the blue strategies, and it means that one less agent is using the brown strategies. This is what we mean by saying that the better strategy will survive at the expense of the poor doers. So in the mutation phase, a small number of the population will be allowed to mutate based on their current strategies. So we can interpret it like they are trying to make a mistake, or they are making mistake, or they are trying to do some experiment with their strategies. So this is the simulation cycle in general. So we have a population, and then we match them to play one shot or repeated game, and then we let them learn and we let them mutate, and the loop will goes on like that. I will show the simulation result for the one-shot game first. We let the population play the Nash demand game, so let PL denote the fraction of population playing low, PM be the fraction playing medium, and the fraction playing high will be the rest of that. And we will represent them on the graphical representation like this. This is the vector field, the replicated dynamics for the one-shot games. We can see that it has 3 interesting rest points, A, B, and C. The point A is the mixed strategies, but it has a very small basis of attraction, and point B has 0 basis of attraction, and point C have very big basis of attractions. So if it's like if we just randomly throw a ball into these triangles, most of the time it will end up in the point C. And also, if we put the ball into the point A, then a very small disturbance of the force, like because this is the stochastic environment, then for example, 10% of people are making mistake, then the ball will just fall into the Bayesian attraction for point C, so it will just end up upwards. And in the other way around, it is impossible to escape point C by making mistake. It requires like 90% of the population making mistake at the same time to escape point C Bayesian attraction. So we say that point C, that in which everybody is claiming mediums, is stochastically stable. And beside that is the simulation that we run, and it approximates the theoretical prediction quite well. So if we plot here the population payout average over time, for the one-shot game, it will be approximately 5 all the time. And so the 50-50 division is very stable across a lot of cycles. This is 100,000 cycles. We can run up to 500,000, and it will be still like this. So you can think of this like the emergence of the convention of the 50-50 division in the societies. Imagine you play this game with the strangers in a different rooms, and you would like to get money home. What would you do? You would think about the others, and you would expect that you will get 5. You expect others to claim 5, and that the left will actually make you to claim 5. And because and it actually happens that when people run experiment on this, the majority of people are able to coordinate on the 50-50 divisions. So the belief will prescribe the action, and the action will confirm the belief, and together they will make the convention very stable in the societies. So this is the simulation result for the repeated game. Across this dimension, it is the number of rounds per match. So at the bottom here, when the rounds per match is just 1, it is a one-shot game. We can see that it is always around 5. However, when the rounds per match increase, it appears that the population average is below 5, sometimes 4, sometimes 2.5, and so these periods appear consistently across simulation. So what happens in those inefficient periods? There are 2 kinds of inefficient periods. The first one is when the population average is around 4.5, and the population is full of top players. They claim high in the first round, but then they retreat to claim medium in the second round onwards. And so the typical payout sequence is 0, 5, 5, 5, 5. And this is to say that the negotiation comes to a very good terms after all, but because it is delayed in the first round, it is costly for everyone in the first round. Now the second kind of inefficient periods has the population average to be about 2.5, which is very low, and there are 2 kind of patterns in these periods. The first pattern is that it is a mixture of top, weak, and flexible strategies. The top strategies always claim high, the weak always claim lows, and the flexibles is the one that will just, if it is matched with a top player, it will just accommodate and it claim lows. However, if it is matched with low players, then it will just keep bullying that players. And the inefficient here comes from the match between the top player themselves, because they always claim 8, they get 0 all the time. And also it comes from when the match between the low player themselves, because they always claim 2. So it means that $6 is wasted all the time. And the second pattern for this kind of inefficient periods is when there are alternators. So they just claim high in the first round, and then they retreat to claim lows, and then they claim high again and low again. So they alternate because no one retreats to claim lows. So they just alternate between high and medium, and the typical payoff sequence is 0, 5, 0, 5, 0, 5. Okay, so that is the result of the simulation that, and I would like to conclude that for the cooperative behaviors, if we are matched with strangers, then everybody will face. But if we are matched with our repeated partners, then we will start to cooperate, and because it is in our interest. However, in the situation of conflicting interest, the repeated interaction actually make it more likely for the negotiation to be delayed and for people to get aggressive in the bargaining process. And it is costly for everyone, for the whole societies when it happens. Okay, so I put here my email so that you can send me question, or my code is available on GitHub. Thank you for listening. Okay.